So, KTU B.Tech Computer Science and Engineering, semester S5 and S6, paper number CS301, paper name Theory of Computation. So, what do you mean by theory of computation? So, theory of computation mainly deals with formal language and automata. For example, if I want to design a machine which accepts binary strings and which ends in 0, so this is what my requirement is. And my input symbol is 110 10110. I need to check whether this particular string ends in 0. If it is ends in 0, this string will be accepted by my machine. If it is not ending with 0, it will not be acceptable. It will be rejected. Okay. So this input string is given to a machine and the machine will start scanning from left to right. Okay. So when it starts from 1, it moves up to the last digit and it checks whether the last digit is 0 or 1. In this case, it ends in 0. So the language is acceptable and it's a language which accepts that particular string. Suppose if the last digit is 1 instead of 0, this string will not be accepted by the machine and it rejects that particular string. So this is what normally how a theory of computation is solving a problem. So we can say it another way. Theory of computation is a branch that deals with how efficiently you can solve a problem. In a model of computation with respect to algorithms. And the algorithms we are focusing are automata theory and language, computability theory, computational complexity theory. Computational complexity theory. So these are the three algorithms used in order to identify the efficiency of solving a problem. Now, the basics theory of computation. The basic theory of computation consists of symbols followed by alphabets, followed by string and the language. So we can consider symbol as a basic building block. So in programming language, we say tokens are the smallest individual part of a program, right? So it can be letters from uppercase or lowercase, digits, zeros till 9. So it goes on, okay? And alphabet notation is sigma, is a collection of symbols. So if I am considering an alphabet of set A, comma B, so these are the input symbol. Now, if I want to have alphabets A, B, and C, so I'll say alphabet sigma A, comma B. Sigma set is equal to 0, comma 1. So it will have an input symbol zeros and ones only. Suppose I want from 0 to 9, I can use that as well. So 0, 1 up to 9. Now comes a string. So we said alphabets means collection of symbols. Now what is string? It's a sequence of symbols. It's a sequence of symbol means it can have a single occurrence of a particular symbol or multiple occurrence of a particular symbol depending upon the requirement of a particular string. Now, so in this case, if I'm using alphabet A, comma B, I can have A only or two occurrence of A, A, B, B. That's a sequence of symbol. Now, a language. A language with respect to an alphabet sigma, comma, A, comma B. So L1 is a language which accepts all strings of length 2. So it will be AA, AB, BA or BB. So these are the strings. Now L2 is another set of language of all strings of length 3. It will be AAA, AAB, ABA, ABB, BAA, BAB, BBA, and BBB. So this is an examples of different languages. You can generate any of the language depending, or you can say two occurrence of A followed by B, two occurrence of B, AA, BB, or A raised to N, B raised to N. Like that, you can say a language. Now, last is a finite automata, that is FA. So you have got a string, you represent that string as W, and W is an element of that language. You'll say it's a finite automata accepting language. If the W is not an element of that language, it will not accept by the finite automata. Now, the next important portion of um, is power of sigma. And here we're considering alphabet as a set A comma B. Sigma 0. Sigma 0 means set of all strings of length 0. Set of all strings of length 0 means epsilon, set epsilon, or you can say it as an empty set. Sigma 1 means set of all strings over sigma of length 1. That is sigma 1. Sigma raised to 2 means set of all strings of length 2. So what if sigma raised to 3? It will be obviously set of all strings of length 3. Sigma raised to 4 means set of all strings of length 4. Suppose if it is sigma raised to n, it will be a set of all strings of length n. Now, what about the number of elements in that particular set? How do you find that? Number of elements in the set can be defined as cardinality of the set. So, in this example, we are considering alphabet A comma B. Okay, 2 elements are there. 2 variables are there. So, obviously, 2 raised to 3, that is 8. So, cardinality of that particular is 8. Suppose what about sigma raised to 4? What is the cardinality? It will be 2 raised to 4. Now, next important portion of power of sigma is sigma raised to star and sigma raised to plus. Sigma raised to star is also called as clean closure, and sigma raised to plus is clean plus. Okay, so clean closure means 0 or more occurrence of that particular input symbol, and sigma plus means 1 or more occurrence. Okay, so the elements are sigma star is sigma raised to 0, sigma raised to 1, sigma, that is set of all strings of length 0, length 1, length 2 up to length raised to n. And sigma plus means sigma raised to 1, that is single occurrence, and of length 1, length 2, length 3 up to length n. These are the power of alphabets. Now, type 3 formalization, finite state automata. Okay, so far we learned about what is theory of computation, the basics of theory of computation, the power of alphabets and all. Now, we are going for the formalization, that is finite state automata. What do you mean by finite state automata? It's an abstract model of a digital computer. So, how can you say it in a simple language? Suppose I need to operate a fan. Okay, we have got two modes, that is on and off. So initially the fan is in idle mode. I need to make it work. So I have to switch on. So from idle state, it is moving to a running state. And from running state, if I want to make it in an idle state, I have to use the other input operator, that is off. So if I am switching on, it will be working. If it is working to idle, I need to put the switch off. So finite automata consists of set of states, okay, and a transition with respect to the input symbol. So transition with respect to inputs is simple, means it is moving to another state. So we can say a finite automata has got what? A state, a transition among the states with response to the input symbol. So in a way, we'll explain it with an example. So consider this as your string. A, B star as your string. So A, B star means what? It can have 0 or more occurrence of B. But occurrence of A is a compulsory. Okay. So this is what A, B star. So A, B star means it can be A or it can be A, B or it can be A, B, B. These are the sample inputs. Okay. So how do I represent this? I can represent a finite automata either by using a transition diagram or by a transition table. Okay. And if I am having an arrow followed by a circle means this is my initial state. And if I am having concentric circle means this is my final state. Okay. From initial state, I should have an input symbol A. It is mandatory that I should consume an input symbol A. And I'm moving to another state that is Q2. Here is the problem, that is whether it should have 0 or more occurrence of B. So I'm giving a cyclic loop of B. Okay. If I need B, I'll come to this state itself. So I'll be in the final state. If I don't need a B, I'll reach the final state. So A is acceptable by this language, this machine. A, B is acceptable. A followed by B, B is acceptable. A followed by B, 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 B is acceptable by the transition diagram. Now, how do we map the transition diagram to a transition table? I have got states, okay, and this is on the vertical and horizontally we have input A and B. Okay, initial state Q1 is represented with an arrowhead. Okay, from Q1 I have got an input symbol A and I am moving to bit state. My arrowhead is moving to Q2 and I don't have any transition with respect to input symbol B. So I just leave it as blank. And Q2, I don't have any input transition of A in that thing. So I just leave the space. Then input symbol B, I'm reaching to the state Q2. So we learned about what is finite state automata, what is finite automata, and where do you use the finite automata. The application of finite automata is happening in lexical analysis. So lexical analysis means it's an important component of a compiler. So when you write a program, we normally terminate each statement with a semicolon, right? Suppose you forgot to put a semicolon, what happens when you compile the program? It shows an error that is semicolon is missing in this particular line number, right? So that is a lexical analysis. It sees whether the string is acceptable, whether it reaches the final state with respect to a semicolon. So if the semicolon is not there means that string is not acceptable, so there is an error. There is a verification occur in that particular case. So finite automata application is a lexical analysis and the lexical analysis is happening in the compiler. That is what it is. Now, we learned about how do we represent the finite automata, right? Now, what is a mathematical specification or the formal specification of defining a finite automata? So, we define a finite automata with 5 tuples, using 5 tuples. So, the components are Q, capital Q. We have got sigma, we have got Q0, that is the initial state, the final state, and delta, the transition function. So Q means the finite set of states involved and sigma means set of input symbols. And we have got Q0, that is the initial state. Okay, and F is the final state. And we have got the transition function delta. So delta means a set of states with respect to input symbol, I'll reach to a state. that is delta function. So we can represent the 5 tuples with the transition diagram, right? So in this transition diagram, the set of states are Q1 and Q2. Input symbol is A and B, set A and B. Initial state is set Q1, final state is set Q2. And what about the delta function? So Q1A, I have a transition of Q1A to which state? Q2. So Q2 is represented over here. And Q2B, I have a transition of Q2 with respect to input symbol B. I'm in which state? Q2. Okay. So that is what the transition function and the mathematical. So we focused about the mathematical specification. How do you represent that in physically? So physical representation of finite automata consists of an input tape. Okay. This is a tape head, and this tape head, the tape is divided in cells. Okay. And we have got a reading head and a finite control. Okay. So the mathematical model has got an infinite tape. Okay, with a finite control. Finite control is a delta transition, and a reading head means it scans from left to right, right? So once it finished the left scanning, it moves to the next state with respect to input symbol. Okay, so why is my input symbol? And it with the finite control, I'm moving to the next, that is my to the right. So always a tape head can scan one cell and advance to the right. And the string, when will be the string acceptable? When the string acceptable happening only when the string is reaching at the final state. Okay. So a string is acceptable by the finite control when the finite control is in the final state. So once it reaches the final state, that string is acceptable. That is a physical representation of finite control. So far we come across the theory, what is the theory of computation, and the basics of theory of computation, and we learned about a finite state automata, the mathematical specification, the physical specification. Now, we divide our finite state machine with the finite automata in two ways. One with respect to output, with output, and other without output. So with output, we have got two machines, that is mode and meaning. And without output, we have DFA, NFA, and epsilon NFA. So today, we are going to focusing about finite automata with output. So we have deterministic finite automata. D means deterministic finite automata. And in order to be a deterministic finite automata, it should satisfy these three conditions. Okay, so what is my first condition? In a DFA, a state does not contain more than one transition. The state should not contain more than one transition. That is my first condition. My second condition is each and every state consume all the input symbol. Each and every state should consume all the input symbol present in the alphabet. Now, it should not have an epsilon transition. Once a finite automata with satisfying these three conditions, it's called a deterministic finite automata. So we can represent our finite automata, we can represent our DFA in a mathematical specification. Same as a finite automata, here also we are having 5 tuples. We have Q, sigma, delta, Q0 and F. So Q is set of states as in the finite automata, alphabet set of input symbol, and delta means delta transition with respect to alphabets and the states, and you moving to another state. And Q0 initial state, F the final state. Okay. Now consider this transition diagram. So suppose if I'm going to see whether this string is acceptable by this machine or not. So 0, 1 0 0 1 0 1. I need to see whether this string is accepted by this machine. So obviously it can say that design a machine which accepts one at the end. Set of all strings accepting one at the end. Okay, so Q00. So if this is my initial state, Q0 is at my initial state. My input symbol is 0. So delta Q0 0. I am moving to which state? Q0 itself. Okay, from Q0, delta Q0 1. I am reaching which state? Q1. And delta Q1 0. I am reaching which state? I am in the Q1 itself. And delta q1 comma 1, I'm moving to bit state q2. Since we have got concentric circle means that string is acceptable by the machine. So 0101 is accepted by this machine. And what is my second condition? How do I understand whether this is a DFA? So first condition of a DFA means it should not have more than one transition with respect to our input symbol. So I have got 0 and 1 as my input symbol and I have only a single occurrence of this. So Q0 0 single transition, Q0 1 it's not to the same transition, so it's accepting the first condition. Q0 are accepting first condition. What about Q1? 0, I'm in Q1 itself. I don't have multiple occurrence. How do I see whether it has got multiple? See whether how many heads are there. Okay, incoming there. Or outgoing, how many are there. Now Q2, 0 and Q2 1. So all the alphabets are consumed by each state and it has not have more than one transition diagram. So the transition diagram is there and we are mapping the transition diagram with respect to transition table. So we have got Q0, Q1, Q2 as states and Q00 means Q0, Q01 I am in Q1, Q10 I am in Q1 itself, Q11 I am going to Q2 and Q20 means I will be Q20 I will be in Q0 state and Q21 means I'm in Q1 state. Okay, so this is transition diagram and transition table of the DFA. Now we have got an important condition while we are designing a DFA. So we mentioned that each and every state should be consumed by an input symbol with respect to alphabets, right? There is a condition called dead state, which means that only incoming transition but no outgoing transition. So it will be in the self loop on the state on all input symbol. Okay. Um, I'll explain with respect to an example. Suppose if I want to design a DFA which accepts strings 1100 only. Okay, I should have only this string accepted by the machine, that is 1100 only string. I didn't say ending with or it should be in the middle or it contain. I said accept this string only. Okay. So what is my first thing means I have to design absolute DFA. So absolute DFA means identify how number of states. So 0. So Q0, if I'm giving 1 as input, I should reach another state Q1. From Q1, I'm giving another input that is 1. I'm reaching to Q2. From Q2, so 1 1 is there. Next input is 0. So I'm going to another state Q3. Q3 again 0. I'm reaching the Q4. That is my final state. So how many states in total? 4 states. Okay. So 1100 absolute DFA is done. Now we have the second condition which states that each state and input symbol should be acceptable. Each state and alphabet should consume all the input symbol. So here the input symbol 1 is satisfied. What about 0? I should introduce another state saying QD. That is dummy state. QD as dummy state. So I'm giving 0. Whenever I'm receiving a 0, I'm giving into a dead state Q0. I mean QD. So it's just having a self. So only incoming is there. Okay. When I'm reaching Q1, if I'm getting a 0 string, I should give that straight away to the dead state. Same to Q2 because after 1 1 it should be 0, it should not be 1. So whenever it is coming 1, I should send it to QD. So the next is Q3. So whenever I'm getting a 1 means I should send that straight away to DQ. No, the dead state. And from Q3, if I'm having a 1, I should send to a dense. And I should only accept one occurrence of 0. If I am having a multiple occurrence of 0 means I should send straight away to the dead state. So all the incoming are there. There is no outgoing with respect to that. So that will be the end. Okay. So this is this is how we design a string that accepts only 1100. Now we are moving to some of the exercises. So design a DFA that accepts the strings that has exactly 3 ones. Exactly 3 ones. In this clause, I didn't mention that this one should be in the beginning or at the end or in the middle. I have no other criteria like beginning, end or in the middle. So the number of ones only will be number of round. The count of number of ones is only 3. Exactly 3 ones. Okay. So first step is to construct a DFA. So my first requirement is 3 ones. So I just mentioned 3 ones as an input symbol and gave the transition. Okay, so this is my input symbol. Now, what is my second condition to satisfy the DFA condition? No epsilon transition. Each state should consume all the input symbol. So there is only one transition. I put the self loop in the Q0, self loop for Q1, and self loop for Q2. So after the 3 occurrence of 1, if I am having another occurrence of 1, what should I have to do? I should send that straight away to a dead state. And from this state, if I am having another zeros followed by another 1, I should be in that state itself. That is in the dead state. No incoming, no outgoing states from Q, dead state. Now, consider the examples. Input string as 0, 1, 1. So if it is 0 means Q0 is my initial state. So 0 input, I am in Q0 itself. If with respect to input 1, I am moving to Q1. Okay. From Q1, moving with 1 as an input symbol to the transition, I reach the state Q2. And from Q2, with respect to input symbol, I reach Q3. So I am in the final state. So this string is acceptable. Now next, 0, 1, 0, 1, 0, 1, 0. Okay. Here also 3 occurrence of 1 is acceptable. 3 occurrence of 1 is there and it reaches the final state. Now 0, I am in Q0. Q0 from 1, I am in Q1. Q1 0, I'll be in Q1 itself. Q1 1, I am in Q2. And Q2 0 means I am in Q2 itself. 1, I am reaching to Q3. And Q3, I am having 0, I am reaching the final state. So this string is also acceptable because exactly 3 ones. Now, if I am having a string like 1, 1, 1, 0. So Q0 with respect to 1, I'm reaching Q1. Q1 with respect to input symbol 1, I'm moving to Q2. And from Q2 with respect to input symbol 1, I'm reaching to the state Q3. And Q3, I'm having another input that is 0. I'm reaching the final state. So this is also acceptable by the machine. 3 ones. Suppose if I am having a string like 0, 1, 0, 1, 0, 0, instead of 0 it should be 1, 0, 1, whether it will be accepted by the machine or not. So 0, I'm in Q0, 1, I'm going to Q1, Q1 0, I'm in Q1, Q1 1, I'm in Q2. So up to this much is okay. And Q2 1, I'm in Q3. Q2 1, I'm in Q3. Q3 0, it is acceptable. Then what is the next one? If there is another occurrence of 1, okay, so I'm in DQ. So I haven't reached the final state. This doesn't accepted by the final state. So it is not accepted. This string is not accepted by the machine. So it's not a DFA. Because we are not having exactly 3 ones, we are having an extra 1 over there. So it is not acceptable. Now, suppose if you want to design a DFA which accept set of strings where number of ones is multiple of 3. Number of ones is a multiple of 3. So, in order to make a cyclic operation, we set the initial and the output as same state. So initial and the output will be the same state. So Q0, 1, 1 and another one I am giving to the same initial state. Okay. So the absolute DFA is constructed now. What about the next step? We need to check whether each state is consumed by the input symbol. It is not. So I'm giving a cyclic loop of 0 to Q0, cyclic loop of Q1, Q1, cyclic loop of 0 to Q2. Okay. So final state we read. Suppose what will be the string? See whether it is a multiple of 3 or not. 0, 1, 1, 1, 0, 1, 1, 1. So 0 means Q0, Q0 1, Q1, I mean Q1 1, Q2, from Q2 again 1, so it's a number of ones means multiple of 3, number of ones is multiple of 3, okay. Now, suppose if we want to design a DFA which accepts a set of strings where the difference between number of zeros and number of ones, that should be a multiple of 3. Okay, so we consider the number of zeros as a cyclic over here. Instead of 1 over here, I put 0 over here. Now, I should get ones as also the number of 3. The difference should be multiple of 3. So, obviously what we'll do, we'll put the alternate over here. Since we put 0 over here, we'll just give an alternate negation of 0, 1 over here to the different direction, opposite direction. Same over here. If this is going to this side, from Q2 I am moving to Q1. So what obviously what will be from Q2 to Q0 it was 0. So I will say Q0 to Q1 as 1. So suppose my input string is 1110 double one double 0. So number of ones are 4 and number of zeros are 1. So 4 minus 1 is 3. Next is 0010. So number of zeros are 4 and number of ones is 1. And the difference we got the number as 3. So in this we learned what is theory of computation, because it mainly deals with formal language and automata. Then basics of theory of computation, that is symbols, alphabets, string and the language. Then we learned about the formalization, that is finite state automata. And in that finite state automata, which is an abstract model of digital computer. And we learned about what is finite automata, because it has got states, transitions with respect to input symbol to another set of state. And there are two variations of finite automata, with output and without output. With output we have Mealy and Moore machine. Without output we have NFA, DFA and epsilon NFA transition. And we learned about DFA, the three conditions to be a DFA. That is, one does not contain more than one transition, the same input symbol. Each and every state consume all the input symbols, and we have no epsilon transition. And the problems based on DFA. hope you understood this portion of introduction of theory of computation and all. Thank you.